Hi students, today in this session we are discussing about the some properties, physical and chemical properties of the heterocyclic compounds. So please like my videos and share with your friends and also subscribe to my channel because I'm not telling it in the beginning of the every classes because I just don't want you to distract from the topics. So please do it. Thank you. And when it comes to the properties, so first we'll discuss about the pyrrole molecule. When it comes to the pyrrole compound, if you see its physical properties, physical properties, so it is a colorless liquid. It is a colorless liquid, and if you see its solubility, it is sparingly soluble in water also. A partial solubility we can see in water, sparingly soluble in water, and as it is also organic aromatic compound, it is readily soluble in organic solvent. Readily soluble in organic solvents. Okay, next, if you see its odor, it is usually have a odor like chloroform. It shows chloroform like odor. Almost all these compounds show chloroform like odor. Even furan also show the same kind of odor. And when it comes to the, as it is a liquid, if you see its boiling point, it is around 131, 129 to 131, or approximately 130 degree centigrade, which is usually one of the higher boiling point for this compound. It is not volatile like furan. Furan is having very less boiling point. So especially because it shows some hydrogen bonding also. So that is why it is having little high boiling point. And it turns, though it is colorless, it turns brown. Turns brown in air. In presence of air, it turns into brown. So it shows little oxidation in presence of air. So this is about the physical properties of the uh, pyrrole. When it comes to the chemical properties of pyrrole, so pyrrole is usually a very weak base. So it shows some reactions of base also, and also it little bit it also act as acid also because it has a higher proton. So it also shows some properties, very weak base and also very weak acid. It shows some amphoteric nature also, and it also undergoes that reduction reactions, oxidations, and some name reactions also. But the very important reaction that is usually asked for 5 marks in your exams is electrophilic substitution reactions of pyrrole, and you also have the same for furan and also for pyridine, which is very important for your exam. For 5 marks it will be as your exam, and now it is NEP in 4 marks. So let us see the only this reaction, electrophilic substitution reactions in pyrrole now. So if you see pyrrole, so here you could see the hydrogen atoms. So these hydrogen only have to be replaced with the electrophile. Okay, so if you see, consider this is a position 1, 2nd, 3rd, 4th, 5th. Okay, 2nd and 5th as usual, the both are equivalent. Equivalent are same. If the reaction takes place at 2nd or 5th, the both are same. As the same for 3rd and 4th position, as these are also equivalent. So we'll get only 2nd and 3rd positions for the electrophilic substitution reaction. So now we have to find out which position, whether second position or third position is more reactive towards the electrophilic substitution reaction. So which gives the more stable compound, then that is the most priority group or position for the electrophilic substitution reaction. As you know, the here one of the hydrogen has to remove or replaced by the upcoming electrophile. So now let us see the positions, whether second position is more gets the more priority or the third position. Electrophilic attack at second position, at second position. So you know, usually in electrophilic substitution reaction there are three steps. The first step is the formation of electrophile. The second step is that electrophile attacks the aromatic compound and it forms a carbocation intermediate, and finally the deprotonation or the removal of that H plus takes place. So it usually having three steps in the mechanism. So when you see, this is the pyrrole. When electrophile, okay, attacks at second position, okay, this electrophile attacks at second position. Let's see here. So this becomes single bond now. Here we got the positive charge, already there is an H. Here the electrophile come and attack. There is also one hydrogen. So this carbocation has been formed. Okay, this actually is unstable, so that's why I'm writing it in a bracket. And this shows the resonance. This shows the resonance. So these electrons will shift here. Okay, when these electron shifts, it gives us this resonance structure. So the positive charge comes here, not here. The positive charge come at this carbon. So when positive charge come at this carbon, this show again one more resonance structure. So this will give electron. Now see, now here the nitrogen has given its electron, so it becomes a double bond. So when nitrogen gives electron, it forms four bond around it. So nitrogen gets the positive charge. So again, it has to, the reverse will takes place. That's why these three resonance structures will be formed during the when electrophile attacks the pyrrole. So now, so obviously at the final step, this proton will be removing. With the removal of that proton, it forms a this compound. Yes, this electrophilic substituted product. So this is about the when electrophile attacks at the second position. Okay, these three are the resonance structures of the carbocation formed during the reactions. Resonance structures. Okay, so when this electrophilic attack takes place at third position, electrophilic attack at third position, or it is also equivalent to fifth position, sorry, fourth position. Third and fourth are equal, second and fifth are equal. Okay, so now let us see when electrophile attacks at the third position. So the electrophile is there, so it has been attacked to the pyrrole now. when electrophile attacks here, so there is electrophile attacks here and there is hydrogen, here also one hydrogen, but here only 3 bonds, that's why it gets the positive charge. Okay, when it gets positive charge, there's a carbocation which is also unstable intermediate, so that's why I'm writing it in a square bracket. So it shows like it also shows again a resonance structure. So this electron will shift to the this bond, that becomes a double bond. Now we'll have this structure. Double bond, electrophile and hydrogen. This nitrogen gets the positive charge. Nitrogen gets the positive charge. But here this cannot give electron because already around nitrogen we have 4 bonds. If it gives electron, yeah, positive charge will not be going because these also become 5 bonds. 5 bond cannot be possible in nitrogen. So that's why we see only 2 resonance structures. Only 2 resonance structures in the case of when electrophile attacks at the third position. So these two are the resonance structures. So finally, here also the same thing. When that proton has been removed, it gives us the electrophile attack at the third position. So electrophile here, yeah, it is two substituted Pyrrole. It is 3 substituted Pyrrole. Okay, so this is about the resonance structures we found in the Pyrrole when electrophile attacks at the second. So this carbocation, and here also we'll have the carbocation resonance. So by seeing the structure itself, you can say now which is the most preferred attack or position for the electrophilic substitution. Yes, the second position is most or more priority for the electrophilic attack, because here we can see the 3 resonance structures, here you can only see 2 resonance structures. So as you know, more the resonance structure, more is the stability. More is the stability. So that's why in the case of when electrophile attacks at the second position, we can find 3 resonance structures, but here only 2 resonance structures. So this carbocation is more stabilized by the resonance, and this carbocation is less stabilized, and among which you can see here, and this one, the third resonance structure, which actually has the positive charge over the nitrogen, which is also unstable. So these two are more stable. So here if you see, this is here also we can see the positive charge over the nitrogen, because nitrogen, as it is an highly electronegative element, it cannot hold a positive charge. This only the one of the stabilized resonance structures, and these two are the stabilized resonance structures. So somehow we second position is the shows the more resonance structures, hence the second substituted Pyrroles are more commonly found, third is not possible. So that's why the electrophile attacks at the second position is the most priority, so it gets the most priority when electrophile attacks at the second position. So this is usually asked in your exam for 4 marks. Please take it screenshot or note it down. The main important thing you should have to mention after the writing the resonance structure, here we get the 3 resonance structures, here we get only 2 resonance structures. So in chemistry, which gets the more resonance structure, that gives the more stable compound. So here with 3, so it is the most priority, it gets the most priority, and here it is the less priority. So, and among which you can this is also helpful because the one of the structure gets the nitrogen, one of the structure in which nitrogen gets the positive charge, here also a positive charge. This is unstable resonance structures. So this is also unstable, this is also unstable. At least you can consider in this case these two, here only one resonance structure which is a stabilized resonance structure. So that's why usually the electrophilic attack or the electrophilic substitution reactions in pyrrole takes place at the second position. The second position is more priority, gets the more priority than the third position. Now let us see some examples of the electrophilic substitutions like nitration and halogenation. Students, this pyrrole is more reactive towards electrophilic substitution reactions even than the benzene. Because benzene, in case of benzene, we can find only two resonance structures. Here we could have seen three resonance structures. Hence, it shows the more reactive towards the electrophilic substitution reactions than the benzene. So, first for example, we have nitration. So nitration means the electrophile here is the NO2 plus the nitronium ion. Nitronium ion. This nitronium ion will replace the one of the hydrogen or proton in the pyrrole. So here also we got the second position is the most priority, hence the nitration takes place at at second position. So one more thing, as it is a more readily undergoing reactions. So here, so pyrrole readily undergoes nitration also. Okay, so here we take nitric acid instead of sulfuric acid. Usually we take nitrating mixture, the mixture of nitric acid and sulfuric acid. So sulfuric acid, it does not needed here, it is not required because it readily undergoes the electrophilic substitution. Pyrrole readily undergoes electrophilic substitution reaction. That's why I'm taking just catalyst like acetic anhydride, CH3 CO CH2 CO CH3, acetic anhydride I'm going to take here, not CH2, it is O, acetic anhydride, and HNO3, acetic anhydride. So which is one of the weak compound, but it makes the, because pyrrole itself is a will easily or readily undergoes the electrophilic substitution reaction. This is enough. We do not need a sulfuric acid as a catalyst. So here we got the product. As you know, the second position is the most prior. The nitration takes place at second position. The nitration takes place at second position. So it is 2 nitropyrrole. 2 nitropyrrole. Okay, that one acetic acid, CH3 COOH. Yeah, 2 molecules. So this is, so pyrrole, when it is treated with the nitric acid in presence of acetic anhydride, it easily or readily undergoes nitration, an example of electrophilic substitution reaction, to give us 2-nitropyrrole. This is a byproduct acetic acid. Okay, the same second example, if you see, it undergoes halogenation also. For example, chlorination, if you take, yeah, this is readily undergo, it is readily undergoing in the case of pyrrole. When it comes to the chlorination, okay, when pyrrole is treated with chlorinating reagents like SO2 Cl2, sulfuryl chloride, sulfuryl okay, sulfuryl chloride. Okay, when it is treated with sulfuryl or sulfuryl chloride, it easily undergo electrophilic substitution reaction in presence of ethers, in presence of ether, a solvent. So it readily undergoes this chlorination. Hence, instead of chlorination just taking place at second position, the chlorination occurs at all the positions, irrespective of its priority, whether second or fourth, the chlorination takes place at all the positions. So it is readily undergoing electrophilic substitution reaction. So even this reaction takes place at 0 degree in cold condition also, it easily undergoing this reaction. So if you name this, yeah, 2, 3, 4, 5, okay, tetrachloro tetrachloropyrrole. So this reaction, why I have written, because this shows it cannot undergoing electrophilic substitution reaction just at second position. The second position is the most prior position, but pyrrole is most reactive towards, or the more reactive towards the electrophilic substitution reaction. Hence the electrophilic substitution takes place at all the positions. This actually gives uh, the reactivity, the high reactivity towards the electrophilic substitution reaction of pyrrole. So these two examples are enough for the electrophilic substitution reaction. Thank you. Thank you for watching. Please like my videos, watch it completely, because then only you will get the complete idea of the syllabus or the topics. And please like videos, share with your friends, and also subscribe to my channel. Thank you.